present on behalf of my team on the approach we took to analyze the 303 datasets and pick the best model for forecasting the next periods in the time series. Our team comprises of Sarun, Rama, Rupesh, Lee, and myself, Arjun. We will go through in detail our objective, datasets, methodology, and summarize our findings. What we will also discuss is the detailed approach that we used to select the best forecasting model and how our forecast looks like based on those models. Our main goal in this project was to come up with a strategy to analyze 303 datasets efficiently. We did achieve that by building an expert model that analyzes the 303 datasets given to us. Throughout our analysis, we used R programming language and ran various models from the ETS and forecasting packages to identify a best model that has the minimum MASE. We then used the model accuracy parameters to perform residual analysis to check for its normality and serial correlation. Using these, we will pick the best model for forecasting the next few periods of the series. The data is taken from the International Institute of Forecasters, which runs a competition called M Competitions. The aim of this competition is to evaluate and compare the accuracy of forecasting methods over a massive collection of 3003 datasets. Today, we will use a different approach for this competition by using a reduced version of 303 datasets. The table here shows the dataset given to us and the count based on the frequency type and the sectors divided. We perform a three-step process on these datasets. First, we extract, transform, and load the data into several time series objects. Since the data has different categories and frequencies, we capture all of these into different objects. Second, we then run all possible combinations of the models using loops and identify the best model. Lastly, we pick a model with the best MASE and then do residual analysis to check for the normality using Shapiro-Wilk test and serial correlation using Lung-Box test. The table shows the various MASE values based on categories along with the mean MASEs for each type of data. We have picked a different model for each type of data based on its frequency. What we have also done is categorize based on the sectors provided to give an overview of that as well. In the upcoming slides, we will discuss the best model for each of the yearly, quarterly, and monthly series. Let us first take the monthly time series data. The plots here shows the best model based on minimum MASE value and the model as multiplicative error, additive trend, and no seasonality. This is a nonlinear state space model which has the best MASE even though it has very negligible residuals that seem to have serial correlation, but still this passes the Lung-Box test. Also, if we look at the normality of the residuals, we see that the model does not pass Shapiro-Wilk's test. Similar to the monthly, let us now see the best model for quarterly data. The best model for quarterly data has additive error, additive damp trend, and additive seasonality as well. This is a linear state space model which has the best MASE value. If you see the residuals plot, the residuals are not serially correlated, but the normality trend seems to be off, but still it passes the Shapiro-Wilk test. Now, let us take the final frequency for the yearly data. The best model chosen for yearly data is the All's optimal model, which basically says that there are no errors or seasonality in the model. The residuals are all normal and they also don't have any significant serial correlations. Previously, we saw the findings based on best MASE value. Let us discuss an example of a model which does not satisfy the residual check for both normality as well as serial correlation. As you can see here, the graph shows serial correlation for the first few lags and it is also skewed as well. So this would be a good example to show the residual assessment check. Based on all of this, we pick the best model and perform forecasting. For this analysis, the model is selected, residuals are analyzed, and we forecast for the future time period. We built a looping system to perform these analysis, and the whole exercise on a normal computer took about 40 minutes only, considering we are running around 40 plus models across each of the 303 data series. Here is a screenshot of the final object we call as the result table that we use to analyze all the data and select the best model based on the lowest MASE value. I would like to end my note by thanking all my team members for their encouragement and effort they have put on this analysis. Thank you viewers for watching. Have a great day.